In the previous module, we talked about the idea of the Anthropocene as a recognition to the fundamental effect that industrial economies are having on the global ecosystem. In this video, we will continue on with this theme by talking about the subject of industrial ecology. Industrial ecology has arisen over the past few decades as the study of these coupled environmental and industrial systems, offering us a systems-based approach to modeling, designing, and managing industrial systems in relation to the natural environment. Industrial ecology as a subject is both interdisciplinary and holistic. Thus, it is a very broad area, giving it a number of different interpretations. The most expansive definitions interpret it in a generalized sense as a means to achieving sustainability. But this is a somewhat open-ended definition. A more common definition would read something like this: industrial ecology is the study of material and energy flows through industrial systems. Or on its most practical level, it may be understood as simply a set of tools for achieving energy efficiency and high environmental standards through life cycle assessment and material flow accounting, among other tools that are commonly used in the field. Although industrial ecology only really came of age in the 1990s, its foundations were laid in the decades before this. Robert Ayers is recognized for bringing together many of the basic ideas that have comprised industrial ecology since the late 1960s. He pointed to the importance of examining material and energy flows in a systemic framework, both in order to truly understand them and to develop effective policies for managing these resources. His work was groundbreaking in that it introduced thermodynamics to the area. Ayers was one of the earliest scientists to bring second-law notions into industrial ecology, and his work stressed the importance of exergy as the proper measurement in studying industrial energy use. The term industrial ecology was then popularized following the publication in 1989 of a seminal article in Science America by Robert Frost and Nicholas Galapagos. Following this event, the field developed during the 1990s and it spawned many academic programs, several journals, and an international society. Today, the influence of industrial ecology is significant and growing, and the analytical tools that are central to the field are increasingly used in other disciplines. Recent publications in top scientific journals signal the coming of age to the field. On a more practical level, industrial ecology principles are also emerging in various policy realms, such as the United Nations and China recently promoting the concept of the circular economy. Probably the foundational and overarching insight of industrial ecology is, as the name implies, understanding industrial economies in relation to and as extensions of natural ecosystems, a recognition that both industrial and natural ecosystems are made from the same basic materials and substances and subject to the same basic thermodynamic principles governing their structure and dynamics. Industrial ecology is based on the same general paradigm as the Anthropocene. That is to say, a recognition that industrial economies are now deeply embedded within the global ecosphere, and that we now need to develop synergistic solutions for integrating the two systems in order to enable their sustainable coexistence. Within this context, industrial ecology can be seen as the practical solution for designing and managing sustainable systems of technology. Thus, a central idea here is that of biomimicry, where biomimicry means the imitation of the models, systems, and structures of ecosystems for the purpose of designing and managing industrial systems. As such, it is an approach to innovation that seeks sustainable solutions to human challenges by emulating nature's patterns and strategies within ecosystems. Natural solutions that have evolved over a prolonged period and have withstood the test of time to prove themselves as sustainable and effective. Industrial ecology includes a number of principles that underpin the subject and form its theoretical foundations, the most important of which include the idea of industrial metabolism, which is concerned with the flow of materials and energy through industrial systems at different scales as described by the principles of thermodynamics. A second major principle is that of systems thinking. Industrial ecology recognizes the need for a holistic perspective when dealing with coupled industrial ecological systems. As such, it is based upon the ideas of systems theory. A third major idea is that of synergies, as captured in the term industrial symbiosis. Here, a primary consideration is how the different components interact with each other and how to design them towards constructive synergistic outcomes. Lastly, and associated with this, is the principle of recyclability and feedback loops, converting linear systems into non-linear cyclical processes through identifying and closing the feedback loops. We'll go over all of these in more detail to get a better understanding of them. As with systems ecology, thermodynamics is the theoretical backbone to industrial ecology. As with ecosystems, the principles of thermodynamics provide the basic supporting context by telling us what is physically possible given the available resources. Industrial systems, and more precisely the global industrial economy as a whole, can be understood and analyzed as a network of industrial processes that extract resources from the ecosystem and transform these resources into commodities that can be bought and sold to meet the needs of human societies. As with ecosystems, the industrial economy is a network through which energy and resources are processed. In this case, we're talking about a global supply network composed of many different nodes, as the resources are extracted, refined, and synthesized during various production processes, distributed through various logistic and commercial networks, and then consumed by end users. Within this context, industrial ecology seeks to quantify the material flows and document the industrial processes that make modern society with its industrial infrastructure function. This flow of resources is also called an industrial metabolism. The idea of an industrial metabolism was first proposed by Robert Ayres. It can be understood as the total use of materials and energy throughout an entire industrial process, such as manufacturing a car or producing a liter of milk. This includes the sources, transportation, use, reuse, cycling, and disposal of all industrial materials, as well as the energy needed at each step. The goal is to study the flow of materials through the economy in order to better understand the complex linkages in our socio-technical systems and the primary sources and causes of waste. Next, systems theory is a fundamental part of the industrial ecology approach. Industrial ecology has been defined as a systems-based, interdisciplinary discourse that seeks to understand emergent behavior of complex, integrated human-natural systems. Coupled socio-technical and environmental systems are invariably complex, consisting of many densely interacting and interdependent heterogeneous components. In such a context, it becomes very important to gain a basic understanding to the overall system of interest on its possible many different levels and a basic understanding for the primary interactions between the subsystems. With this holistic view, industrial ecology recognizes that solving problems must involve understanding the connections that exist between the systems. Various aspects cannot be viewed in isolation. Often changes in one part of the overall system can propagate and cause changes in another part. Thus, you can only understand a problem if you look at its parts in relation to the whole. Narrow analytical reasoning in such complex systems can often lead to simply moving a problem from one place in the system to another without any net gain. Another key idea within industrial ecology is that of material and energy cycling. As observed within the many cycling processes found in ecosystems, where resources are continuously cycled through the system. Industrial ecology is very much concerned with the shifting of industrial processes from linear, open-loop systems in which resources and capital investment move through the system to become waste, to a closed-loop system where waste can become inputs for new processes based on a natural paradigm, claiming that an industrial ecosystem may behave in a similar way to the natural ecosystem wherein everything gets recycled. On the macro level, this takes the form of the circular economy. The circular economy is grounded in the study of feedback loops and nonlinear systems. A major outcome of this is the notion of optimizing the cyclical processes in the system rather than components, resulting in a focus on function and the services that deliver those functions instead of the discrete products themselves. As a generic notion, it draws from a number of more specific approaches, including cradle-to-grave design and life cycle assessment. The central idea is switching from an open-loop model of take, make, and dispose industrial processes and consumption that creates a dead-end effect, towards trying to identify and close these loops in enabling a more self-sustaining economy. Coupled to the idea of feedback loops is that of industrial symbiosis, where symbiosis means a mutually beneficial relationship between the different components of a system. Industrial symbiosis is a subset of industrial ecology with a particular focus on material and energy exchange through initiatives that are aimed at achieving sharing and coordination among diverse sectors of an industry. As such, industrial symbiosis looks at engaging diverse organizations or industrial systems to create networks that foster reusability, collaboration, co-innovation, and other forms of synergistic exchange. A simple example of this would be a wastewater treatment plant providing cooling water for a power station, and the power station in turn supplying steam for an industrial user. Another example would be the use of tire shred or plastic pellet waste from a factory output that can be sold onto other businesses as valued inputs. In this way, industrial symbiosis systems can collectively optimize material and energy use to achieve efficiencies beyond those achievable by any industrial component alone. Self-organizing symbiosis is a model where an industrial ecosystem emerges from the decision by private actors in meeting such goals as cost reduction or revenue enhancement. The industrial initiative typically starts small in a bottom-up fashion, and if successful, more follows, often out of ongoing mutual self-interest. In the early stages, there may be no consciousness by participants of the industrial symbiosis or inclusion in an industrial ecosystem, but this can develop over time. The project can be strengthened by more formal frameworks for cooperation after initial successes. A classic example of this is the Kalundborg symbiosis, an industrial ecosystem in Denmark. Here, several linkages of byproducts and waste heat can be traced between numerous entities such as large power plants, an oil refinery, a pharmaceutical plant, a plasterboard factory, an enzyme manufacturer, a waste company, and the city itself. The industrial symbiosis at Kalundborg spontaneously evolved from a series of micro-initiatives over a long time scale in a bottom-up fashion. The engineering design and implementation of such systems from a macro planner's perspective on a relatively short time scale would prove highly challenging. As the Kalundborg Symbiosis organization itself said, systems make it possible, people make it happen. In the development at the Kalundborg Symbiosis, the most important element has been healthy communications and good cooperation between the participants. The symbiosis has been founded on human relationships and fruitful collaboration between the employees that have made the development of the symbiosis system possible. Finally, we'll briefly touch on the more practical models and methods used within industrial ecology. as the field has a strong anchor in engineering and includes substantial elements of environmental management. Life cycle design and assessment is a primary model used that tries to assess the impact a system has over its full life cycle and design processes based upon this analysis. Material flow accounting is another method, which is an analytical tool for quantifying flows and stocks of materials or substances in a well-defined system. Typical applications of MFA include the study of material, substances, or product flows across different industrial sectors. Environmental input-output analysis is another method used in environmental accounting as a means for evaluating the linkages between economic consumption activities and environmental impacts, including the harvest and degradation of natural resources. As such, it is becoming an important addition to material flows accounting. Likewise, on a social level, stakeholder analysis is a primary tool used in the field for identifying the many parties that may have a stake within a particular project or industry. In this video, we've been taking a brief overview to the domain of industrial ecology, a relatively new interdisciplinary area that takes a holistic perspective to the modeling, designing, and management of coupled ecological and industrial systems, an approach that looks at our industrial infrastructure from the perspective of natural ecologies and biomimicry. We talked about some of its basic principles, including the idea of industrial metabolism, representing the flow of materials and energy through the industrial system at different scales. Systems thinking, which recognizes the need for a holistic perspective when dealing with these complex engineered systems. We talked about synergies and how the different components interact with each other and the overall system. Recyclability and feedback loops, converting linear systems into non-linear cyclical processes through identifying and closing feedback loops. Lastly, we briefly looked at some of the models and tools used in this area, including life cycle analysis, input-output analysis, material flow accounting, and stakeholder analysis.